Now we're going to talk about a little bit about hardware, and you guys, I'm sure you've seen all these things, but we'll talk a little bit about each kind of. There's other kinds of pumps, but these pumps are commonly used in irrigation systems. You can have more than one pump on an irrigation system. In fact, having two pumps is, I would say, is common. A lot of times you'll have, you might have a vertical turbine pump here pumping water out of a well and feeding a piping system, and then each pivot will take water from that piping system and deliver to the pivots. And so you might have a vertical turbine pump there in the well, and then a centrifugal pump feeding the pivot. So the centrifugal pump is probably more common. I'm thinking it's probably the most common. Basically, if you're splashing somebody in the swimming pool with your hand, you're doing the thing that you're impelling this water, okay, with your hand. And so the pump actually has a series of it's a little paddle wheel, and it's the water comes in the end here of this, and this impeller is spinning, and the spinning of this impeller literally is just like splashing water with your hands. It forces the water to the outside of the pump, and that increases that pressure, and the pressure comes out. The outlet is here. The turbine pump is really a series of centrifugal pumps, if you think of it this way. There's a number of, they're called bowls, and there's bottom bearing, and the water level is maybe in here, and so these are below the water level, and each stage, each bowl increases the pressure to the next level, then the next level, the next bowl takes it up to another level. So these would be for more high head. Head is the vertical column of water. For higher head, higher pressure, for volume. And this is just one stage, okay? So these are also called stages, so it's just a one stage, so you can get a maximum amount of power, of pressure increase. A third kind of pump we see, and this is a jet pump, okay? And so the concept that I try to tell people about this is think about the Miracle-Gro no clog feeder, okay? You screw this thing onto your garden hose, and when you turn it on, it slowly feeds the chemical out of the feeder and meters it into the water and sprays it out. And it uses this principle. It's a venturi, so as the water goes through a convergent, divergent nozzle, the pressure is lower here than here, and it draws the water in. So the jet pump actually recirculates water through the pump, but it draws water into the system, and that's the water that flows out. And not very efficient because you're moving a lot more water than you're actually delivering, okay? And there's a couple of different kinds. Sometimes they put this venturi down at the bottom of the well, and they can only go about 30 feet deep. They can't go very deep because what's actually pushing the water into the system is atmospheric pressure. So you can't go more than 15 psi pressure, 30 feet. So sometimes the venturi is built right into the front of the pump. So these are generally smaller. The centrifugal pump, I say high volume, low head. Turbine pump is high head and low efficiency, but it's fairly versatile. We can, these are small. There's usually, here's some real pictures. of these things. So this one, the Venturi is built right into the front of the pump. So you can see this is a fairly small unit. You can just pick it up and move it. So that's the benefit. Here's a couple of vertical turbine pumps. This one that we looked at down here is a vertical turbine pump. We've got another picture of that if you want to see it. And this is a picture of a centrifugal pump, also being used as a foot rest. So this is about as gnarly as I get with math, but the power for irrigation pumping, the equation or the relationship is very simple. Okay, it's just the head, the vertical water column, the pressure that you're making, multiplied by the flow rate. Okay, so you know, and where it gets tricky is the different units of measure. So if you have flow rate is usually in gallons per minute, and the pressure is usually measured in feet. Okay. Then here's the relationship. The power is the head times the flow rate, but then you got to convert the units. So to get the power in watts, you have to multiply. You know, how do you get feet times GPM into watts? Okay, that's the problem. So flow rate, gallons per minute, times density of water. Okay, 62.4 pounds per cubic foot. All of a sudden you're starting to see feet in along with feet. Okay, so that's why we like feet. Multiply the acceleration of gravity, feet per second squared. Okay, then we convert gallons to cubic feet, because this one, we got to get rid of this gallons thing. And we end up with, this will get us to foot-pounds per minute. We convert foot-pounds per minute into watts. There's 44 foot-pounds per minute is a watt. Okay, so I'm glad we're through that, because I know you guys hated it. Wasn't that fun? That's as bad as it gets, honest. Because everything else I just relate to computer models. So anyway, it's the same relationship with hydroelectric power. So if we've got a pump, we're putting power into the pump to push water up. Just the same equation is we get water at a higher elevation coming down at some flow rate. We can make power with it. Okay, it's the same relationship. When you start talking about pumps, each pump has its own pump curve. And the manufacturers print these out, or you can get software programs online that will generate these for a certain pump. And so this particular pump, it's a generic pump. The pumps are all measured in the diameter of the impeller. Okay, these are some centrifugal pumps. 10-inch diameter, 8-inch diameter, 6-inch diameter. This is head. Okay, so this is feet of vertical pressure, and this is the flow rate. Okay, so at the trivial condition is at no flow rate, no pressure, you get nothing, right? So as the pump is, say, going faster, the flow rate increases, the head increases, okay? This particular pump has, these are the efficiency curves. So for an 8-inch version of this pump, it is most efficient. Here's 60% efficient, 55% efficient, 50% efficient. This location here on the pump curve, this flow rate, this pressure, the pump is the most efficient. So, not to get too far ahead of myself, but if your system pressure and flow rate matches this location, you're at a sweet spot, and that's the most efficient you can get. Okay, what's common is the flow rate is less, the pressure's higher, and the efficiency is going to be lower. Okay, so this is how, when we talk about how we can go through the system and measure up all these losses and everything, this is coming up. I know that you're fascinated. And then we take that head requirement, the requirement of the system, and the pressure requirement of the system, and we can plot it on this and see where this pump is going to operate.
So how would we adjust to move around there? So say you're too much pressure.
Let's
So if we were like,
Lots of spreadsheets.
Okay.
Figure out why it's not efficient.
so do you slow the pump down?
You might slow the pump down.
If
Okay.
we were up by
Yeah,
the
yeah.
55 number instead of down in our optimal point for the 8-inch.
Yeah. So what would we do?
Yes.
We're going to try to move.
If you're trying to move from 55 to
Yeah.
60 on say the 8-inch line.
Okay. Well, let me get to the system curve. That'll help, because otherwise I'll stand up here and I'll. System curve is this is what the pump is serving. So this is the system out past the pump. So this one, we normally have some static head. So the pump is we want to generally keep the pump as low as we can, okay? So then we're pumping up into the system. Anything that's always there, that's always vertically above the pump, that doesn't change, that's called static head. That doesn't change. And so ideally, if the pump is delivering right into the system and it's all on the same level, then there would be no static head. But that's rare. There's almost always some static head. Then as the flow rate goes up and the pressure goes up, there's the system curve heads up because there's losses. There's friction losses, and so as the flow rate goes up, it takes more work to push the water through it. So here, and we've got some changing conditions. Let's see. So if we add a sprinkler or something where we add more head or more flow rate, it's going to drop the pressure. Or if we have, over time, the systems can get scaled up and get crudted up inside, and maybe the inside diameter of the pipe is actually smaller than it was when it was new, then you'll get higher pressure and less flow rate. Okay, so these indicate changes to the system. So the system is new, it's great, you know where everything is, but over time the systems change. The systems always have losses. Now, calculating losses is a challenge, okay, and this is something that you can do as an exercise to the student. This is after we have supper and go to the bar for a couple hours, then we can do this kind of thing for fun. Look up how to calculate these losses because it's bizarre, okay? But we have software programs that are, free that we can get online. Now the thing about these software packages or these calculators is if you find this one happens to be something called, I'm not making this up, pressuredrop.com. Okay, so you find this little calculator here, you pick the fitting that you're doing. Okay, you got to do this for everything, okay, and this is sort of it's an accounting thing or a laundry list thing, okay? So you have to start at the inlet of the pump and every little piece of pipe and every little elbow and restriction and fitting and valve and everything. You have to add all these up, okay? So you do this for each one. Put the inputs in, and it'll tell you what the output is. Normally, the outputs will either be in inches or feet. This is pressure drop, so it'll be either in inches or feet, or it will be in equivalent feet per 100 foot of pipe, okay? And so you have to be a little bit aware of the units that you're in. This one is kind of cool because it puts the output in PSI, okay? So you can convert PSI to feet, okay, of water or inches or whatever. So you have to know a little bit about water. One of the things it asks you for is kinematic viscosity, and kinematic viscosity is in and of itself is this bizarre number that, people that cooked this stuff up here, a lot of years ago, they didn't have a lot to do, let me tell you, because this stuff is really cold. But it has to do with the properties of the fluid. You can use the same methods for any fluid, but of course we all use water. This is the form for a straight piece of pipe, just straight pipe. Picked 100 feet, 100-foot pipe, 6-inch pipe. I tried to standardize on 6-inch pipe because it was 455 gallons per minute, and it was something about a 1/10 of an acre inch. And I mean, there were things I liked about that I could kind of remember about a 6-inch pipe. But 100-foot, I think that this was plastic pipe. Plastic pipe is common. Water, I couldn't change 20 degrees C. You couldn't, so 20 degrees C was what we got. But water's incompressible. There's not a lot of difference between 20 degrees C and 0 degrees C water, or 1 degree anyway. Volume flow, what's that?
A little difference, right, at 0.
At 0, yeah. 6% in specific volume, yeah. Yeah, and also it turns solid.
It's a little hard.
Yeah. Hard water. Yeah, but the killer in freezing is the 6% less specific volume, because that shows up and it breaks the pipe. Yeah. Water's about the only thing that does that. How about that? Nothing else does that. Wow. Gnarly.
Canning jars too full and you freeze them, it'll do that.
What, candy bars?
Canning jars.
Canning
Can
jars.
things and you freeze it, freezer canning,
Yeah?
it'll break jars. if you
Really, it will.
don't
Maybe
do
it's
that.
probably because there's water in there, huh?
Probably.
Yeah, okay. Well, enough digression. Enough digression. These are fun, though. That water's the only thing that does that. Yeah. And it's lucky that it does that, because if it didn't, water wouldn't freeze the way it freezes, because right now, I mean, water freezes from the top down. Okay, right? Yeah, because it's lighter. Ice is lighter. It floats on top. So if it didn't do that, everything would die. Yeah, we're lucky that water works that way, and it's the only thing that does that. Okay, so anyway, I did 2 runs of this. It just only takes a second to do each little piece of pipe. You do each little piece of pipe, so it takes a while to march through this. Okay, so I did 2 runs. One of them at 5 feet per second velocity, which is a rule of thumb. This is kind of what we want to hang with, 5 feet per second. And one at 10 feet per second. To show that at 5 feet per second, which is a good design point, we have about a 1/2 pound per square inch drop in 100 feet of pipe. Okay, so we lost a 1/2 PSI. At twice the volume, twice the speed, we've dropped 2.2 psi. So 4 times, we increase the flow twice, we increase the losses 4 times. Okay, so that's where you start getting into some of these design issues, where if you can show that you're pushing too much water through this pipe, and we can put in a bigger pipe and have we can cut the losses way down, we can cut down the size of the pump. Okay, so anytime you have you'll see a big massive pump and a little pipe, that indicates to you that maybe we've got some inefficiencies in the piping. Okay, you do this, like I said, you do this for every bend, divergent sections, convergent sections, valves. Pivot systems are, you go to the pivot guy and say, what's the pressure drop in the pivot? You can calculate through the pivot, whatever they are, 6-inch or 8-inch pipe, and calculate those losses. The sprinklers, and I say, yup, everything. You've got to do every last little stinking piece of pipe. You know, so it's not necessarily difficult. I mean, with your laptop, and you can crank those out pretty quick, but if you've got, 10 elbows and, a couple of valves and, an intake structure that comes up, and it's got, you have to add all that stuff up. Okay, so you start out with the water requirements of the field. So you got the crop evapotranspiration thing divided by the field efficiency. So that gives you how much water you want to apply, and for over a period of time. So that's how much volume you need. The system operating pressure is dictated by the sprinklers. So the sprinkler needs so much pressure to work. And this is where we're talking about the end guns. I think they need more pressure, and they're generally bigger. They have a bigger orifice in them than those little drop sprinklers. And so they're bigger, okay? So they need more power to get the water, and they're way out there on the end. So, yeah, but in any case, every time you take water out in a sprinkler, you have to say, well, this, and you start at the end, and I was gonna draw all this out. Should we just, I know that you guys love this stuff, but here's, let's see, let's draw this. Let's just draw it like this, okay? And so these, I'm just going to kind of do like this, saying that these are sprinklers. These are generally 30 inches apart, right? This is typical? It's 30 inches in between sprinklers? I don't know. So maybe this is a 6-inch pipe, and we've got an end gun here or something, and this spraying out like this. 30 inches between the sprinklers, between the drops. Is that typical?
That doesn't seem far enough to me.
Yeah,
It's
further apart.
I think it depends.
It depends on the crop, for sure.
Right.
Okay, but I thought I read something someplace that said 30 inches was typical. Anyway, that's neither here nor there.
I think
Yeah, I can't reach them usually.
In between them, yeah. Okay.
Yeah, I think so. Yeah, I was thinking about 60 And you wonder why you have a little strip where one doesn't work. Yeah.
Okay, so anyway, this is my system. And I put 2 pumps in it. This is, now, there's something that you have to think about with the well. When you're pumping water, and you know, if you're pumping it out of a ditch or something, you're not going to see any difference in elevation. But if you're pumping it out of a well, you're going to have a difference in elevation between when the pump is running and when the pump is not running. Okay, because the water tends to do this. I didn't draw it very well, did I? Okay, it literally sucks the water down. Okay, so what do they call that? There's a name for it. Maybe they call it the static well level or something like that. Anyway, the well logs or the well driller can tell you this. So you have to know where this water level is here. And then this is, I drew a pump here. So you're going to have some pressure and some volume here. You've got to account for this piece of pipe for losses. Then you got this piece, this elbow, assuming this is straight. Let's see, now we're going to have a valve here. Okay. What else are we going to have? There's probably there's almost always like a convergent, divergent section here and here, so you have to watch for those. Anyway, the moral of the story is any fittings in here, you have to do this. This is an elbow, this is an elbow, this pipe here, and these are probably different sizes of pipe. Okay, this might be a 10-inch, maybe 8-inch here. This might be changed, this might change diameters also. They're not necessarily the same. So, and then you want this, so you've got to satisfy the pressure here. So there's a pressure gauge here, so you can measure the pressure here. You've got to satisfy this sprinkler, so whatever sprinkler you've got there, you can look it up in the catalog and find out what its pressure requirement is. Then you have to add the losses all the way back. This pump, you have to satisfy all the pressures that these guys need and the volume of each one of these guys. And I think the catalog has, for each sprinkler, it has the pressure that it likes to work at and the volume. Okay. If it doesn't have the volume, it certainly has the cross-sectional area. Okay. So the area, the volume is the area times the speed of it, the velocity of the water. These are in the catalog. So
That's why it's absolutely possible to just gas the pivot.
yeah, my theory is this thing's. Sorry, folks. I lost I broke it. I broke your mic. Yeah, I would certainly basically at the pivot, I would be working with the pivot guy saying, what's the pressure drop in this pivot? And because they will have that information, be able to tell you. Okay, so that's how you relate the pumping volume and head to the volume, which is acre feet on the ground, the rate of application, and the pressure that you want at the pump is the pressure from the last sprinkler plus all the losses. That's going to give you the operating point.
So what do we have going on if all the heads are fine, there's no plugs, but yet we're getting our crop's not very uniform because we don't have enough pressure out of a couple of those, either at the end or in the middle of that. What do you think's going on there?
And you said the nozzles are fine?
The nozzles are fine. I mean, they're not plugged. Could that be that they're
Well,
worn, maybe?
yeah, they're going to be worn. Yeah, the nozzles last like 3 years.
Right.
I
So
would think a worn nozzle would distribute more water though,
the
not less.
okay, well, okay.
Well,
I wonder.
Does that affect your non-worn nozzle output?
Well, okay. This is the system. This is the system curve.
The reason not worn as well, where the non-worn ones are or where the worn ones are.
So this is a system curve. So worn nozzles are going to let more flow through, and the pressure is going to be less.
okay.
So that's going to be down here. If the nozzles are plugged up, or somehow restricted, or the pipe is corroded inside and it's a smaller inside diameter than it should, the system curve is going to be higher. The pressure is going to be higher, and the volume is going to be less. So if you've got a lack of uniformity, I would say if the nozzles aren't plugged up, then they're worn, because then the inside, the diameter of the orifice of the nozzle is bigger, and I've seen that. I think that's pretty common, where because it's not just water going through this thing; it's dirt, so they do erode. And I think that I read something that said replace them every 3 years, and I hazard a guess to say that people don't replace them every 3 years. Yeah. The other thing to remember is this goes a lot farther than this, and so you have to have a bigger nozzle out here than you have in here. But these are kind of design considerations, and there's sort of a lot of different variables, and so I didn't want to really get too much into that, because it's sort of beyond the scope of my intelligence. So,
And your pivot should have come with the right sprinkler heads at the inside and the outside.
yeah. Well, and it should have been. I'm sure that if you get into some of these really old pivots, I mean, what were they designed or patented in about 1950? So there's some old ones out there, and they might be some pretty screwy designs, and they might they might use the same nozzle, but space them closer together out here, something like that, or use a bigger nozzle. So there's all kinds of different design considerations that, but I think, what we can focus on is, the overall system, because I don't, if the water is uniform and you look and you don't see a lot of runoff, then I think that you could, be as confident as you can that it's not the pivot, And if it's the pivot, then you would see that in uniformity. You'd say, well, geez, we've got some of the plants are this high and some of the plants are this high, and so the plant water, these guys are not as happy as these guys, so we need to figure out how to get them more water. But then I'd probably pass it off onto the pivot guy. Just a little bit on sprinklers, because the sprinkler systems themselves will have pressure, not pressure loss, but volume loss, because this is where your water is going. So they're measured in different ways. They can be measured in 128ths of an inch in diameter. Okay, so if you see a 28 size is 28 128ths in diameter. They also come in fractions of inches, and these are like the end guns. The impact sprinklers do this, and the drop sprinklers, I think, do this. I don't want to start lying to you guys. I said, when did you quit? Pipe sizes, 6 to 10 inches, and if it's, and like I say, a quarter mile pivot is typical or common, but we've got them in Montana that are more than a half a mile. Yeah, I'm sort of partway through an irrigation audit on a half a mile pivot, which is a big pivot. It was the biggest pivot in the state for a long time. Flow regulators, they do have, and I read a couple of different kind of conflicting things. They said, okay, first, if the field is flat, okay, if there's no elevation change across the field, then you might not have flow regulators in the pivot. But if it's on a hill, then you'll have flow regulators. And flow regulators are just like pressure regulators in your house. They're spring loaded, and if the pressure drops, they open up a little bit, and they make sure that 40 psi or whatever the pivot pressure is maintained. So you guys have seen these things. I might have a picture of them in here. And I see that the slides are a little out of order, so I apologize for that. This is going to be a little quirky, but I kind of wanted to go through the idea. Where did I drop? Oh, this is part of the microphone. Yeah.
I thought you were doing a squish test.
Yeah. We want to show how the system curve and the pump curve interact with each other a little bit, and you guys are all going to fall asleep in this part anyway, so it doesn't matter if the slides are out of order. One of the things, and I'm going to get to this combined thing, but say our system curve or our operating point is maybe out here. Okay, we've got a real high flow rate, and maybe we're not getting the pressure that the sprinklers like. Okay, so and the combination of these is we have less efficiency. Okay, these are the efficiency lines here. So we can say that we're too low of pressure, so the nozzles are worn. So the pressure is too low. We put new sprinklers on, it moves us up this curve. The system curve is coming up like this, and our efficiency is better. And so the system is happier. So that, I don't know if...
So when you're doing this, are you recommending that you change all your nozzles to comply? Because everything's going to be worn, like you said.
Yeah, I would say
Then
change them all.
You just want to go through and
Yeah.
make sure everything's cleaned up.
Yeah, I think so. It would be fairly compelling to say, well, the ones out on the end are going to wear more because they got more going through them. But, I think probably it would be something that say, okay, at the beginning of the season, I'm just going to replace the nozzles.
But who does that?
Nobody. But I'm just. That's from a practical standpoint.
Well,
But that was my question, though.
Well, but
because,
the thing is,
when
is
you do it with sprayers and spray nozzles, I mean, it's recommended that you switch
Right.
them all out instead because of the same thing
Yeah.
and wear and tear.
Yeah.
Where it doesn't make any sense. Yeah, you have one that's working, and the other, quarter of a mile or
Well, yeah,
not
if they're,
working as
if they're
efficiently.
not, yeah. I mean, I think if one is plugged up, I think you can take it off and back flush it and probably clear it out.
Right, I mean, as far
If
as
it's
plugged,
plugged,
but
yeah.
I
Yeah,
mean,
but if they're worn out,
3 years
you're,
of
yeah,
wear.
you're stuck. Yeah, you gotta replace them. Just like the losses, the pump manufacturers all have software to help you select the pump. So, and I picked a very unfortunate example pump. This is actually a sump pump, but but you can, and you know, Gould's, it's called Pump Selection Software, PSS. And man, I'll tell you what, it just takes a long time if you don't, like I was just guessing pumps. And if you have a pump that you're looking at in the audit, you could put it in the software and it'll know all about it, okay? But since I was just kind of guessing at pumps, I didn't want to take a lot of time to just come up with a background slide. But it's got all these things that we were talking about, that you know, the GPM, the pressure, you know, that you want, and this is from the system. So, you know, the moral of the story is you start way out at the end of the system and work yourself back to the pump, and now we're at the pump. Okay, so here's the manufacturing. Manufacturers have this software that have all the. You pick the pump, you pick. You know, the suction pressure you can calculate from your losses on the suction side, all the stuff that you know about it, and it will generate a pump curve and an operating point for that pump. And I was looking around for one of these and couldn't find one that I was really happy with, and so I just used this generic one instead. Yeah, and so you can use the software, or you can tell the sales engineer. You can say, hey, I've got a system out here that looks like I've got this, I have this pressure requirement and this flow requirement, and I've got a pump. I don't know what it is. Can you help me figure out what pump would be the best pump? And they'll do that. So again, you superimpose the system curve on the pump curve, and if the nozzles are too big, you can put smaller nozzles on, move them this way. It might be if you've got, now we've got to think about this a little bit. It could be possible to move the system curve either way to get into this efficient point. It's probably a matter of losses in the fittings. Look for fittings that have very rapid transitions. Those are evil. You want everything to be nice and smooth, all the radiuses to be big to minimize those losses.
In old systems, I think, when we were in Phillipsburg, we talked about the fact that in old systems, sometimes the pump's not big enough. And so the pump curve it's really inefficient because the pump's not the right size.
Yeah, it could be the pump is not the right size. So if the operating system is here and the pump curve is here, you see you got very low efficiency.
Yeah, but I mean, if your pump is too small for the job, you're going to fall down below that ideal system curve. It's going to be below efficient if your pump's too small.
Yeah,
Because
well,
the pressure will be
and
lower.
yeah, and this is, it just says 60, 55, 50, but it gets less and less efficient all the time. Yeah, so yeah, and this is something that you'll see every now and then. Okay, and then they weld that. That's a pipe. That's an elbow. So that's a evil one.